Okay, so we'll continue on here. So just a few more key points about R, okay? So I guess I'll just write a few key conceptual points about R, or the correlation. Okay. The correlation between x and y is the same as the correlation between y and x. Equal to the correlation next. So we can ask, is there a correlation between, so just let's say we're just assuming our data set is just dealing with heterosexual couples, okay, so male and female relationships. Is there a correlation between the height of the male and the height of the female? Yes, no, positive, negative, zero? Okay, well, think about that for a second, okay? What if I switched it around? Is there a correlation between the height of the female and the height of the male? Positive, negative, zero? I would argue you would see a positive correlation, okay? Because overall, and this is not the case for everyone, but overall, men who are shorter generally are in relationships with women who are also shorter, and overall, women who are taller are in relationships with men who are taller, okay? Just overall as a broad trend, okay? Of course, everyone is different, individuals are different, and of course this is just limiting ourselves just to heterosexual couples. So if we were talking about if there is some kind of positive trend between the height of the women and the height of the man, then we will see that exact same correlation if we switched the variables around height of the male and height of the female and things like that. So just in, well, anyway, so sometimes you might see two variables and think that they are not related, but if you flip them around, you might think, oh, maybe there actually is a trend, and you have something like that, okay? That's, the correlation is probably not going to be very strong at all, okay? But I think there is a little bit of a trend there, okay? Okay. So switching the order of the variables does not affect correlation, okay? Another one is adding a constant or multiplying by a constant, okay? So adding and subtracting is the same thing as adding, right? It's just adding a negative number, okay? So adding a constant or multiplying by a constant. And again, division is the same thing as multiplication, just does not affect R. So, if we asked what is the correlation between some people's height and their weight, okay? Correlation between height and weight, and we measured in the, American units, customary units, okay? If we measured height in inches and weight in pounds, okay? And we found the correlation to be, 0.7 or something like that. I'm just making that up. If we switched to metric units, okay, to height in centimeters and weight in kilograms, the correlation would be exactly the same, because changing from one unit to another is really just multiplying by a constant, okay? Even switching units in terms of temperature is just multiplying by a constant and adding a constant, okay? So changing units is just either adding or subtracting or multiplying or dividing by a constant. So when we do that, it's things are unaffected. Okay, so changing units will not affect so you can switch between kilograms and pounds or inches and centimeters. That will not affect your correlation. Okay, the correlation itself is unitless. Okay. And again, correlation only makes sense if the relationship is linear. You must, okay, so you must check to make sure is linear to use correlation. Okay. But again, you can still calculate correlation. Correlation can be calculated for any data set with two numeric variables. It's just that the interpretations of the correlation will not make sense unless the relationship is linear. Okay, so I should say correlation can be calculated for any data set with two numeric variables. Okay. Okay, are we ready? Let me, you're just waiting, okay. Okay, let's try a little problem here. Multiple choice question, okay. So we will say the relationship between x and y has a correlation of r equal to 0.8. This means that okay, and we'll have a few options here, and we'll say choose which are true. Okay, we'll say the relationship is moderately strong. Okay. Larger values of x will correspond large y, or there is a negative, really strong negative, and moderately strong linear relationship. not enough info to answer. Okay, so think about your answers here. Answer or answers. Choose which ones are true. Could be one or more. Okay, do we, what do we decide? Anybody? You guys have been deceived, and the answer is not enough information to answer. Okay, I just the last thing you wrote on the previous slide was must check to make sure the relationship is linear to use correlation. Okay, and nowhere here does it say the relationship is linear. Okay, so you don't know that the relationship is linear, so you can't say that it's moderately strong or that larger values of x correspond with large y. Okay. If it said the relationship between x and y is linear and has a correlation r equal to 0.8, then yes, A and B would be true, okay? But we do not know if it is linear. If the relationship is linear. Okay, if it were linear, then A and B would be true. Okay, but and it's important that you know, as I set up this question, just to kind of drill the point home that you must know that the relationship is linear. Okay? All right, let's talk about linear regression where we are modeling trends, okay? So when we say modeling a trend, it's like, you know, you can think of building a model airplane, okay? A model airplane is supposed to be a representation of what an actual airplane is, okay? It's not a perfect representation. It's not a real airplane, or, you know, it's just kind of like a smaller version that gives us an idea of what the big version looks like, okay? Or, you know, if you're an architecture student, you have to build these little models, okay? That is supposed to be a representation of what the actual thing is going to look like, okay? So we can model trends with linear regression, and so what we are trying to do is we are trying to create a model or a representation of the actual relationship between X and Y in the population. Okay. So we're trying to come up with a model of what the actual relationship is between X and Y in the population. Okay. So the example that we will use is here we're going to we're going to look at a bunch of our data set consists of books. Okay, so we're looking at books, and we're measuring how thick or how wide the book is. Okay, so the width of the book. Okay, and we're going to try to predict the width of the book based on how many pages are in the book. Okay, so we And so we're going to try to create this model using a linear equation, okay? You know, as we get into these things, we're going to, the linear regression model will look something like this. Y hat is equal to A plus BX, okay? So this is called Y hat, and this represents our predicted value of Y. It's not Y itself, but our prediction for Y, okay? So the hat is just kind of like a little modifier that we put on the variable to say it's related to this thing, y, but it's not the actual y. Okay, so here we're trying to say it's not the actual y, but it's our predicted value for y. Okay, A is going to be our intercept, and B is going to be our slope. Okay, and x, of course, is our x variable. So in this case, when we are trying to predict the width of a book based on the number of pages, our line is our thing is going to be width with a hat to say our prediction for a book's width is based on some intercept plus b times the number of pages in the book. Okay. So basically our predicted width is equal to, you know, A plus B times the number of pages. So here we're trying to model the relationship between the width of a book and how many pages, okay? And this relationship, this model makes sense because if you think about a bookshelf and you've got really wide books and little, you know, narrow books, in general, the wide books will have lots of pages and the narrow books will have very few pages, okay? And so it makes sense that when we increase the number of pages, we can kind of predict the width, okay? And so you might have the slope could be positive or the slope could be negative, okay? And so according to the math that we will come up with, okay? So here are kind of our predicted width, or width hat. Will equal 6.22 plus 0.0366 times pages, okay? Width is measured in millimeters, okay? Okay, pages is just a simple count. All right, so if a book has 100 pages, what do we predict the width to be? So how do we answer this? Well, you just plug this in. Okay, so you would do width is equal to 6.22 plus 0.0366 times, and in for pages we're going to plug in the value 100. So I can just type in 6.22 times 0.0366 times 100, and I get 22.765. Okay, so our predicted width is equal to 22.7652. Did I miss something? Did I mess something up in here? Oh, I did. Yeah. Okay, thank you. So it's not that, but it's 9.88. That makes more sense. I was like, that number looks kind of big, but okay, so we got 9.88. Great. Okay. All right, what if a book has 200 pages? Width for 200-page book? And what about the width for a 300-page book? Okay, for 200, our predicted width would be 6.22 plus 0.0366 times 200, and I get 0.13 or 13.54. Okay, this is our predicted width. Oh, I got to write predicted. And predicted width. What's our predicted width for a 300-page book? Okay, well I'll do the calculation myself, and we get 17.2. Okay, so far so good. Okay, let me ask you another question. How much did our prediction increase when we went from 100 pages to 200 pages? Okay, and what's your answer there? Okay, we added 3.66 millimeters, right? Okay, how much did it change when we went from 200 to 300? And you would say it went up another 3.66 millimeters. Okay, so what if I just add a 400-page book? What would you predict? We would predict what? 17.2 plus 3.66, and we would get 20.86, right? And we can test this out. We could do we can plug it into the original formula, and we would get 20.86. Okay, this is not magic. This is the interpretation of the slope. Okay. What we see is that the slope is 0.0366, okay? So our slope is equal to 0.0366. And that means every time I increase the number of pages by 1, my predicted width goes up by 0.0366 millimeters, okay? But of course, adding 1 page is we're adding very little to it. So it's hard to kind of picture. I have a hard time picturing what 0.0366 of a millimeter is, okay? But on the other hand, if we talk about, adding 100 pages, okay, I just multiply 0.0366 by 100, and so that means we're going to increase the width by 3.66. I'm sorry, we're increasing our prediction by 3.66. And so every time I add 100 pages to the textbook or the book, our prediction goes up by 3.66 millimeters, okay? So the slope, and I want this, okay. So the interpretation of the slope, okay, this is if we increase x by 1 unit, we predict y to increase by the slope. Okay, so over here we had, predicted width is equal to 6.22 plus 0.0366 times pages, where, x is our pages. So the interpretation here is basically if we add 1 page to the book, okay, add 1 page to the book basically is increase x by 1. Okay. We predict the width to go up 0.0366 millimeters. Okay, so this is, we predict y to increase by the slope. Okay, and of course, sometimes it makes more sense to multiply x by some factor that puts the amount of y into context here. So it would be, if we add 100 pages, we predict the width to go up 3.66 millimeters. Okay. Here we're just talking about a prediction though, okay? And so if we compared 2 books and one book had, 500 pages in it and another book had 600 pages in it, it does not necessarily mean that the 600-page book will be exactly 3.66 millimeters more than the 500-page book, okay? These are just predictions. So overall, we're expecting 600-page books overall to be on average 3.66 millimeters more than 500-page books. But, for any pair of books, there might be a difference, okay? And so the difference between the actual value that we observe and the value that we are predicting based on our model, that difference is called a residual. Okay? So, our predictions are not necessarily 100% accurate. Okay? The difference between our predicted value, or I'm sorry, between the actual value and our predicted value, is called the residual. Okay, and so we can say residual is equal to actual minus predicted. Okay, symbolically, we use the term E for residual, kind of like an error. It's like the difference. And the actual value is Y. And what is the symbol we use for our predicted value of Y? Y hat. Okay, so you might just see E is equal to Y minus Y hat. So for example, we can say, you know, predicted width is equal to 6.22 plus 0.0366 millimeters. Okay, we'll say a book that is 150 pages long is 9.2 millimeters thick, or 9.2 millimeters wide. What is the residual? Okay. So to answer this, we would say, well, first we got to figure out our predicted width. Our predicted width is 6.22 plus 0.0366 times 150. So 6.22 plus 0.0366 times 150, we get 11.71 millimeters. Okay, and so our residual is the difference between the actual value of 9.2 minus our predicted value of 11.71, and so we get a residual equal to 9.2 minus 11.71, we get negative 2.51. Okay, so this means our book is 2.51 millimeters thinner than what we predicted. Okay, and so that is, this is what a residual is. Okay. The other value that appears in our equation is the intercept. Oops, this should actually say pages, not millimeters. Sorry about that. All right, so the other value is 6.22, and this is our intercept. Okay, the intercept is our interpretation, or I'm sorry, the interpretation of the intercept is our prediction for the width if we could plug in 0 for y, x. Okay, so the intercept is our prediction for y if we can plug 0 in for x. Okay. And so in this case, it would be, you know, if a book has 0 pages, we predict the width to be 6.22 millimeters, okay? So maybe this could loosely be thought of as how thick the covers are. Okay, but in many cases, it does not make sense to plug in 0 for x, and in that case, the interpretation will not have a meaningful, the intercept will not have a meaningful interpretation, okay? Okay. So in those cases, yay? Okay. All right, so let's talk about, how do we come up with the slope and the intercept, okay? So calculating the slope and intercept. Slope and intercept for our regression line. Okay. Well, the regression line tries to minimize the sum of squares of the residuals, okay? So maybe I'll just illustrate something, okay? So let's say we have this, and we have a few data points here. Okay, and the intercept is basically you're taking these residuals, which is the difference between our prediction and okay, and we're squaring these residuals, so we're going to square these. So I'm drawing little squares here. And we're trying to minimize the total sum of squares between the line and the residual. Okay, so some other line might have much larger. Okay, so these are the squares of the residuals. And this week's lab, you'll take a look at the squares of residuals. Okay. So as we the best fit line minimizes the squares of the residuals, okay? And you'll explore this in the lab. And basically, when you do that, the slope and intercept will always end up having the same formula, okay? The way then, so because math, the slope and intercept will have the same, will end up with the same formula. Always end up with the same set of formulas, okay? The slope and intercept can be determined so the slope is b, and this will be r times the standard deviation of y divided by the standard deviation of x. And the intercept is going to be a, and this is going to be y bar minus b times x bar, okay? And the best fit line always passes through the point x bar and y bar, so the mean of x and the mean of y. Okay. So this is how we calculate the best fit line. And in your lab this week, you will encounter these things here. Okay. Are there any questions on this? All right. Okay. So let me end with just a few warnings about regression. Okay. So regression, linear regression is it's a very useful tool, but there are a few words of caution. Okay. Okay. So do not use linear regression for nonlinear models or nonlinear relationships. Okay. And that seems obvious, but people try to do stuff. Okay. So I'm going to say also beware of outliers, okay? All right, so let's say we had, we looked at the relationship between shoe size and SAT score. Okay, so we have shoe size and SAT. And so overall we see no trend, okay? Okay, let's say Shaquille O'Neal took the SAT and he got a perfect score. Okay, so he ends up, I don't know, out here. Okay, so suddenly, because this guy's an outlier, the best fit line is going to try to fit that, okay? And we're going to suddenly see a positive trend because Shaq has really big feet. And if he gets a perfect score, then we're suddenly going to see a positive trend. Where in reality, there is no trend overall between shoe size and SAT score, but because of the outlier in the data, it might appear that there's a positive trend. Okay, so this is kind of the true relationship, and this will be the apparent relationship because of an outlier. Okay, so watch out for something like that. And another thing is, do not extrapolate. Okay, or basically do not make predictions for places where you have not collected data. Okay, so let's say some scientist, quote unquote scientist, let's say this guy has a kid, and he measures the height of his child from age 3 to age 10. Okay, so we're going to look at the relationship between age and height okay? And every year between ages 3 and 10, he sees his kid growing, okay? And maybe there's a very strong linear relationship between, age 3 and age 10. We're seeing this very strong linear relationship between age and height, okay? And so our researcher might be tempted to conclude that by the time the kid grows up and is 50 years old, he will then be, 25 feet tall or something like that, okay? And we know that's very silly, a silly thing to do, right? To expect that this child is going to continue growing at this same rate all the way into the future, okay? Because we know from experience that, sure, as a, in your youth and in your childhood, you keep growing, but then around, at some age, age 15 or age 20 or whatever, at some age, you stop growing, and this is kind of the height for the rest of your life until your bones start to get weak and you start shrinking in height and things like this, okay? This is something we expect, and we recognize that this would be a ridiculous thing to try to use the trend from age 3 to age 10 to try to predict the future, okay? We recognize that that's ridiculous in this scenario, but in many other contexts, in many other scenarios, you hear people saying like, for the past 20 years, we've seen this trend, which means by the year 2050, this is what's gonna happen, okay? And that thing can only be said that this is the way the world's gonna look in the year 2050 if the currently existing trend continues. But the reality is that anything is possible in the future, okay? We might see this now, okay, but in the future it could continue, or it could level off, it could shoot up, we don't know. It could even go down, we don't know. So it's what happens in the future, we don't know, okay? So don't extrapolate to places where you have not collected data, okay? All right, we'll end there. We'll see you guys on Wednesday.